This is officially the last lesson for Gen Chem II, and it's on nuclear chemistry. There will be no problem set for this unit. If you understand everything that's in the lesson, and you understand the review packet that was given out around Easter break on nuclear, then you should be fine for any question that you would get on the exam. Most of what we're going to cover is a review of Regents Chem with only 2 or 3 little twists, but not difficult. So let's review types of particles. First of all, an alpha particle is a helium nucleus, and it can be written 2 ways. It can be written 4,2He, or it can be written 4,2 with the alpha sign. A beta particle is simply an electron. It can be written as an electron symbol, or it can be written as 0, -1, B for beta. A positron is a positive electron, so 0, 1e or 0, 1b plus. This is also written as B minus or B plus. They all mean the same thing. Gamma particle is no mass and charge, and it is has the strongest penetrating power, and it is 0, 0. So gamma is the strongest and alpha has the least penetrating power. Neutron, 1, 0, N, and then a proton, 1, 1, P. You determine the nuclear stability, so you're looking at the ratio of your neutrons to protons. In very small atoms, that is going to be a 1-to-1 ratio, but as the atoms get larger, this can change. As you on your graph probably can see, you've got for mercury, you've got 1.53 to 1 ratio, and it is still within the belt of stability. This right here, this area, this is all the belt of stability. So as the nuclei get larger, you can see that the number of neutrons increases in order to keep it stable. This is from your book. It just reviews different types of radioactive decay. I'm not going to spend a lot of time on this, but you should know that when a particle undergoes alpha decay, the resulting particle that forms is going to have less mass and less charge than the original one. In neutron emission, when the neutron is ejected from the nucleus, the only thing that's going to be changing is the mass. The charge will stay the same. Spontaneous fission, that's when 2 smaller nuclei unite to form a larger one. This happens in the sun. We'll talk about that a little bit later on. Positron emission is also known as beta positive decay. The nucleus emits a positron and a neutrino, and we'll talk about what that is. Electron capture is when a nucleus captures an electron and emits a neutrino. The daughter nucleus is left in an excited and unstable state. And then you can also undergo electron capture with positron emission. So in that case, if it's positron emission, then it would emit 1 positron and 2 neutrons. And you don't have to memorize these. This is just different types of decay and what's going on. Just a general overview. But I would like you to understand in beta particle production what's going on. This is something that's relatively new to you guys. So you have a neutron that turns into a proton and in the process emits an electron. So you have 1, 0, N turning into a proton and emitting an electron or a beta particle. In electron capture, it's basically the opposite. You have an electron combining with a proton to produce a neutron. So we have 0, -1, B plus 1, 1p, yielding a neutron. Remember when you're balancing nuclear reactions that the mass on the left must equal the mass on the right, and the charge on the left must equal the charge on the right. I'm going to go through these relatively quickly because this is a regions concept and you should be able to do this. So if I have 6 plus 2 is 8 on the left and I have 4, this has to be 4. So the 8 matches up. 3 and 1 is 4. If this is 2, this is 2, so this is just another alpha particle. Or it can just be simply written as 2, 4, 2, He. Here we have strontium, and this says a mass of 88, and it has an atomic number, which we get from the periodic table, 38. You have krypton with a mass of 84, and it has an atomic number of 36. So over here you have palladium with an atomic mass of 116, and it has an atomic number of 46. So we need to figure out what this particle is going to be. So if you do the math here, you've got 172 on the left and 116, so this has got to be 56. And to balance your charge, this would have to be 28, which is nickel. Calcium's 4020. Curium is 248. This is 248, 96. Over here we have samarium, which is 147, 62. So we have 248 and 40, which is 288, and 147, so this has got to be 141 to get it up to 288. And then we have 96 and 20, which is going to be 116 minus 62 is going to give us 54. And that's going to be Xe. Here we have calcium again, 4020, uranium 238, 92. Zinc is 7030. Here you have 4 neutrons, 1, 0, 4 of them. And the mass is 1, so you've got 4 times 1, which is 4. Plus this, 70, is really 74. And on the right there, you've got 238 plus 40, which is 278. So this has got to be 204 for my mass. And then over here, you have 112 minus 30, which is going to give you 82, which is going to give you lead. And this lead is stable. So things undergo continual decay until they reach to a stable state. Sometimes you'll see it written like this, alpha decay of iridium 174, so that's IR 174, and the atomic number of iridium is 77. It's telling you it's undergoing alpha decay, so it's releasing an alpha particle. So this is going to be 170 and 75, which is Re. We have platinum, PT, 199. The atomic number is 78, and that undergoes beta decay, 0, -1, E, which is going to give you 199 and 79. Remember that whenever beta is involved, your atomic mass increases by 1, because this is negative, and that's going to be gold. Well, look at that. Well, we already know we cannot make gold from platinum. It'd be nice if we could. Positron emission from sulfur-31. We have sulfur-31, has a mass of 16. Positron is my positive electron, and that's going to give me 31 and 15, which is phosphorus. I believe we have one more. We have Kr, 76, has an atomic number of 36, electron capture, meaning it's taking an electron into its nucleus, and we're going to wind up with 7635, which is bromine. So you need to know how to write basic decay reactions. Okay. This is showing you, and your diagram and your notes is a little bit different, but it's showing you the decay, if you look at all the way at the top, of uranium 238 all the way down to lead 206. Because the lead 206 is stable. And so uranium will spontaneously decay and keep going until it gets to a stable form. Now, what I would like you to do, I'm going to show you how this works, but this can all be found on table 18.3 on page 849 in your text. I'm not expecting you to write all these down. I just want you to understand what's going to happen. So I'm going to start here. Uranium 238, 92, and table 18.3 tells me it undergoes alpha decay, which is going to give me 234, 90, which is thorium. And then 234, 90 thorium undergoes beta decay, and that's going to produce 234, 91 Pa. 234, 91 Pa undergoes beta decay, and that's going to produce uranium 234. Uranium 234 undergoes alpha decay, and that produces thorium 230. Thorium 230 undergoes alpha decay, and that produces 226.88 Ra, and that undergoes decay. Alpha also, and that produces 222.86 radon, and that undergoes decay. Alpha as well, producing polonium. Polonium undergoes decay. Alpha again, and produces 214.82 lead, which is not a stable form of lead. So it continues to decay. Beta this time, and produces 214.83 bismuth. And that undergoes decay. Beta, forming 214.84 polonium. And that undergoes alpha decay and produces 210.82 lead, also not stable. And that undergoes beta decay, producing 210.83 bismuth. And that undergoes decay, 210.83 bismuth, which is going to be alpha decay, and produces, oh, my mistake, was not alpha. Jumping the gun here. That was beta again. and that's going to produce 210, 84 polonium. And the last one, that's the one that undergoes alpha decay and produces 206, 82 Pb. And this is stable, which is what we said up here at the top. Now, if we wanted to write one reaction, we could start with the U-23892, U-23892, and that underwent, let's go back and check how many alphas. 3, 4, 5, 6, 7. Did I miss any? Oh, 8. So we underwent 8 alpha decays. How many beta decays? 1, 2, 3, 4, 5, 6. Plus 6 beta decays, and we produced 206, 82 lead, which is stable. So this is our final equation. So it's going to continue to decay until it reaches a stable state. And again, all these particles, the decay mode came from the table in your book on page 18.3. Okay, let's talk about some neat equations that we can solve with it. First of all, we talked about radioactive decay when we did rate laws and kinetics, so that's old news. And we can use these equations to help us determine how much stuff is left. So if you remember N, let's recall N is the amount of radioactive particle, and your NO is the initial amount that you started with, initial amount of radioactive particle. Okay, so we can use the ln of N over N initial equals negative KT, where K is your rate law constant, T is your time. Or we can use T to the 1/2, so that your half-life is the amount of time for 1/2 of the sample to decay is equal to 0.693 over K, or rate equals the rate law constant, if we want to figure out rate, times the amount of radioactive particle that you have left. So technetium-99 is used to form pictures of internal organs in the body and is often used to assess heart damage. The rate for the technetium-43 is known to be 1.16 times 10 to the minus 1 hours. What is the half-life? So we have the rate constant, so this is our K, and they want to know half-life. Well, we're going to use this formula, and we are going to solve for the half-life. So T to the 1/2 equals 0.693 divided by 1.16 times 10 to the minus 1 hours. And we solve for this, we're going to get 5.97 hours. Very straightforward. The half-life of molybdenum is 99 is 67 hours. How much of a 1 milligram sample remains after 335 hours? So we have time elapsed and we have half-life. So we can take 335 and divide it by 67, and that will equal the number of half-lives. So that's going to be equal to 5. And they want to know how much is left. So I have to undergo 5 half-lives of a 1 milligram sample. So half of 1 is 0.5, half of 0.5 is 0.25, half of that is going to be 0.125, half of that is going to be 0.0625, and my fifth half-life is going to leave me with 0.03125 milligrams. So this underwent 5 half-lives. Each arrow is a half-life. 1, 2, 3, 4, 5. In the last problem, a wooden artifact from a Chinese temple has a carbon-14 activity of 24.9 counts per minute as compared with an activity of 32.5 counts per minute for a standard 0H. So whenever you see counts per minute, they are talking about a Geiger counter. And a Geiger counter measures the amount of carbon left in a substance. So as carbon decays, as the amount of carbon in the substance decreases, the less that it lights up. So it would have less counts per minute. So you can see here when it started, it was 32.5 counts per minute, but as the carbon decayed, now we're at a point where it's only 24.9 counts per minute. So there's two things that we need to use here. We're going to use our ln is of n over n initial equals negative kt, and we're determining age. So basically time, we're solving for time. So if I'm solving for time, I'm going to have, we're going to just divide both sides here by negative k. So we got that divided by negative k, and that will give us time. But we also have to use t to the 1/2 equals 0.693 over k, because we need k. So what do we have? We have 0.693 over k, and this is 57.15 years, because this is our half-life. And when we solve for k, we get k equal to 1.21 times 10 to the minus 4. So over here, we now have the ln of n, which is what we have now, 24.9, over n initial, which was 32.5, equals negative 1.21 times 10 to the minus 4 t. So we're going to divide the ln of 24.9 divided by 32.5 by negative 1.2 times 10 to the minus 4, and we get t equal to 2,201 years. So that's how old the artifact is. All right, I'm going to talk briefly about a few more things and then wrap it up. How is radioactivity detected? Well, the easiest way is through a Geiger counter. And it detects the amount of radioactive particles by using different probes for different types of materials. And it can detect how old things are. So anything with carbon in it, we can detect how old it is. Medical, we use it in X-rays. We also use it in biomedical tracers. We talked about titanium. Another example is iodine 131 is used to detect thyroid problems, and it's used in energy to harness nuclear energy. And we do that through nuclear reactors that produce heat, an extreme amount of heat, which is converted to steam, which can then be used to run turbines. Okay, so what gets scientists so excited about all this nuclear stuff? Well, basically, you can produce a whole lot of energy from a very, very small amount of mass. And I'm not going to ask you to calculate this, but I just want you to understand what we're talking about when we're talking about a ton of energy from a small amount of material. Mass of H, so this is the proton, and the mass of the neutron. And this is a mass, an actual mass of an oxygen atom. So we know that oxygen has 8 protons, 8 neutrons. So let's calculate the mass of oxygen based on that. So we're going to have 8 times 1.67262 times 10 to the negative 27 plus 8 times 1.67493 times 10 to the negative 27. And that's going to equal 2.67804 times 10 to the minus 26. So if I calculate the mass of oxygen based on the mass and the number of protons and neutrons, I get 2.67804 times 10 to the negative 23 kilograms, which is different from what they have listed here. The actual mass of oxygen is 2.65535 times 10 to the negative 26. I made a mistake here. This should be 20. This should be 26, sorry. Negative 26. There we go. So what is this difference? This difference is 2.269 times 10 to the negative 28. Lost somewhere. Well, this is called the mass defect. Now, we can figure out how much energy this equates to, because we know, thanks to Einstein, that energy equals mc squared. So let's take this mass, 2.269 times 10. I think I made another mistake. Hold on. I'm sorry. This head cold has got me really not thinking straight. The exponents are the same, so don't ask me what I was thinking here. So this is also negative 26. Now we're back on track. All right, so 2.269 times 10 to the negative 26 times the speed of light, 3.00 times 10 to the 8th squared. And this gives me energy in the realm of 2.04 times 10 to the 11th. Now, this was kilograms, and this is meters per second squared, which is going to give me a joule per atom. So if I want to convert that to energy per mole, I just have to times it by Avogadro's number. 6.02 times 10 to the 23rd. And this is going to give me 1.23 times 10 to the 18th joules per mole. And I could divide that by 1,000 and turn it into kilojoules, and I get 1.23 times 10 to the 10th kilojoules per mole. That is a ton of energy. Lots of energy. Now, if we were to compare this to, say, the energy of CH4, which is negative 882 kilojoules per mole, what's going to produce more energy? Well, hands down, nuclear fission. Okay, so let's talk about nuclear fission really straight from Gen Chem, fission, division. When large nuclei split or divide. So you've got uranium-238, which is pretty big. It's bombarded with a neutron, which causes it to split into 2 fragments, which then releases 3 neutrons, which then go bombard 2 more U-238s. And they're broken into fragments, each producing 3 more neutrons, and the process continues. And you wind up with a chain reaction. In fusion, which happens in the sun, fusion, unite. So when small nuclei fuse together. So here you've got tritium, which is a hydrogen with a mass of 3, and a deuterium with a mass of 2. They unite and they produce helium, and in the process they give off a neutron. All right, how to build a nuclear bomb. Not that we ever would, or that we could, because you can't even get the materials, but what's actually happening when this takes place? Well, you have the chain reaction. You have a neutron which bombards uranium, which then produces 3 more neutrons, because we don't worry about those fragments, which then go and bombard 3 more uraniums, and ... So there's your chain reaction. Now, this chain reaction can only happen when you have enough mass. You have something that's called subcritical, and this is having less mass than what's needed to keep the chain reaction going. Then you have what's critical mass. Critical mass is enough mass to keep the chain reaction going. And then we have supercritical, where this chain reaction speeds up to the point where it goes out of control. And the reaction is the reaction that you have there. It's the same one we've been talking about. All right. Lastly, what are they doing when they create the bomb? How are they getting all the pieces together at the right time? Well, you have a couple of different types. You have what's called a gun type assembly method, in that here you have 2 subcritical pieces of uranium-235. So this is one on the left and this is one on the right. So if they're subcritical, it's not going to be enough to keep the chain reaction going. But what happens is, if you have an explosive device and it's fired, it causes these 2 subcritical halves to join together under high pressure there, and you've got a supercritical mass. And that's enough to get it going. The other type is the implosion assembly method, where you surround, in this case they have a plutonium core, and you surround it with explosive devices, so that this plutonium gets shoved together under high pressure and high velocity, which also creates a supercritical mass. Once you have a supercritical mass, then you've got the speed and the reaction will take place. All right, lastly, in a hydrogen bomb, you've got your tritium and you've got your deuterium, and that's going to produce your helium and a neutron. Well, this is what's going on up in the primary end, and it's going to collect neutrons. Once you have enough neutrons, that can then be added to the secondary part, and then the neutrons bombard that subcritical mass and turn it into a critical mass, and you wind up with this over here. All right, so that's about it. We grazed nuclear, and that's all you have to know. So review this and review the note packet, the other note packet I gave you on nuclear, and you'll be fine. And again, no problem set for this. And I will put up information about Monday's lab tomorrow.